We are going to present you the Munkres assignment algorithm. It was developed by Harold Kuhn in 1955 and then reviewed by James Munkres in 1957. It attempts to solve the assignment problem. But what is the assignment problem, you might ask? The assignment problem requires that a number of jobs is assigned to a number of workers such that each of them does exactly one job. The initial setting of the problem can be represented as a cost matrix, as the one on the left, where each entry shows the cost of that worker doing a specific operation. Solving the problem by brute force on an n-by-n matrix would result in computing all the sets in order to find the minimal sum independent set. Thus, the complexity is given by the number of all the possible independent assignments. There are n choices for the first assignment, n minus 1 for the second, and so on. Therefore, this approach has an n factorial runtime complexity. Fortunately, Harold Kuhn and James Munkres ran into the same problem and developed the Munkres assignment algorithm, which solves the assignment problem in polynomial time.
In order to allow for a better understanding, the algorithm will be presented while working on a particular case. Suppose that a product is manufactured after getting through a series of 6 operations. Also, there exists the same number of workers and each of them is qualified to perform any operation, only that a worker can be faster or slower than another on a particular task. To optimize the overall time spent on finishing a single product, tests have been conducted and the table captures the final measurements where, for instance, worker 3 performs operation 4 in 7 minutes. The goal is to find that optimal worker operation allocation in which the product is successfully produced in minimum time. The Munkres assignment algorithm consists in a series of steps that will finally lead to the solution we are looking for. In step 1, we build a square matrix M by copying all the elements from the table. We can notice that operation 1 takes at least 2 minutes to be done, operation 2 at least 3 minutes, and so on. Therefore, in step 2, we have to find the minimum element of each row and then subtract it from every element in each row. Thus, M1 is obtained. Now we check if we have at least one zero on each row and each column, which is the purpose of this step. If not, we have to repeat the same operation for those columns that don't contain a zero. Pay attention that we'll work on M1 now. So from columns 1, 2, 3, 5, and 6, we subtract their minimum elements. At this point, we have at least one zero per row and per column as well. We'll see later on how these zeros lead us to the final answer. Also, as we subtract a number from all of the entries of any one row or column, the algorithm correctness remains intact. An optimal assignment for the resulting cost matrix is also an optimal assignment for the original cost matrix. The next three steps will determine the appropriate rows and columns to cover all the zeros entries of the matrix such that a minimum number of rows and/or columns is used. Thus, let's proceed with step 3. Here we modify the matrix resulted from step 2 according to the following rules. First, we choose the row that contains the least number of zeros. If there is more than one, we'll pick the first one from top to bottom. Choosing a different row at this step will finally yield a different configuration of assignments, yet the total cost will remain unchanged, having the same minimum value. So it's up to you here. After that, we have to inframe the zero whose column has the least number of zeros. Again, if there is more than one, we'll pick the first one from left to right. Now we have to cross any zero that is on the same row or on the same column with the zero we just inframed. We have to repeat A and B until every zero is either inframed or crossed. Also, bear in mind that at any time, only those zeros that are not yet inframed or crossed are considered. Finally, there will be at most one inframed zero per row and per column. If there are n inframed zeros, in our case we look for 6, then we have a minimum cost, perfect matching, and stop. If not, we go further. Let's work this out for our case. We notice that there are 3 rows, all containing just one zero. Rows 3, 4, and 6. We'll pick the first of these and inframe it 0. Also, we cross all the other zeros that are either on the same row or column. Not all the zeros are covered, so we repeat the same steps. The first two rows both contain a single zero. Remember, the zeros already covered are not considered, so we inframe the first zero and cross other zeros accordingly. We do it again for the fifth row. Inframe and cross. We don't have the required number of inframe zeros, so we proceed with step 4. Here we have again a set of rules that must be applied to our last matrix. First, we have to mark all the rows that don't have any inframe zero. Therefore, we mark rows 2, 4, and 6. Second, we mark the columns that have at least one crossed zero on a marked row. We distinguish columns 2 and 4, and we can see that columns 4 has 3 such zeros. Ultimately, we mark the rows that have an unframed zero on a column that we previously marked, so we mark rows 1 and 3. We don't repeat the process again, as there is no crossed zero on rows 1 and 3, which could correspond to an unmarked column. Also, if there is no B, there will be no C, and we are done here. In step 5, we simply have to draw lines on every unmarked row and on every marked column. Thus, we mark row 5 and columns 2 and 4. Also, we have managed to reach our goal, determining of a minimum number of rows and columns that cover all the zeros. You can notice that we have the same number of inframe zeros, which is not a coincidence. Remember that if we had had 6 inframe zeros from the first place, we wouldn't have reached this step. Next, in step 6, we first have to find the lowest element of the matrix that is not crossed out by any line. As you can see, our minimum such entry is 1. Then we add this value to the elements that are crossed out twice. Thus, this 0 becomes a 1, and this 2 right here becomes a 3. Now we have to subtract the same value from every element that is not crossed out by any line. These are actually the elements which we selected our minimum from. Notice that the elements crossed by a single line remain intact. Now, having a new matrix, we go back to step 3 and try our luck at finding enough inframe zeros. We use exactly the same rules we applied before. The last row is a single one that contains only one zero. We inframe it and cross any other zero on each row or column. Finally, after managing to cover all the zeros, we can remark 6 inframed zeros. That means we have found an optimal assignment for our initial coast matrix. At this moment, the only thing we have to do is to bring forth our initial coast matrix in order to sum up the corresponding costs of the inframed zeros. 30 is the minimum cost in our case. Once again, the diagram in the bottom left illustrates the pairs of our perfect matching. Selecting different zeros at the point mentioned above could lead to different assignments, yet having the same minimum cost.
Now let's quickly recap the steps you need to follow. Make sure you notice that you can only stop at step 3. When thinking about the runtime complexity, for step 2 it's O of n squared because in the worst case you need to go through all the elements in the matrix. For step 3, the worst case scenario is that you have to go through all the elements in the matrix n times, thus leading to O of n cubed. Step 4 is also O of n cubed because all the elements could be 0, which would lead again to n iterations of all the elements. Step 5 is O of n because you have to check the unmarked rows and then you can check the unmarked columns. Step 6 takes O of n squared because in the worst case, the number of uncrossed cells is almost equal to n squared. Overall, the total runtime complexity is O of n cubed.